Howdy, folks. Welcome to CS128 Honors. Today is another lecture covering parallelism and concurrency and how to use threads in Rust. First, a motivating example. So suppose we have a list of customers' birth years, and we want to figure out their ages by subtracting birth years from the current year. As you can see from the problem and from the code here, this is an order n algorithm. We always require a loop through the VEC because we need to calculate the ages for every customers. Can we actually do better than this? So a potential solution is what if you could divide up the customers into multiple groups and calculate the ages for each group in parallel. So which means that the time needed will be just the length of each group instead of the length of the entire set of customers. This is actually achievable in most modern languages, including Rust, using parallelism and concurrency. But this is a jargon, so what do they actually mean? So concurrency, it means that we run multiple computations called tasks at the same time. These concurrent tasks may finish in overlapping time periods in no specific order. And parallelism, it just means that we execute multiple subtasks of the same task at the same time. What is an example of these two concepts? Well, this is a computer. We have multiple tasks. That means programs running at the same time. And each of those tasks may have multiple subtasks. An example might be browsers with multiple parallels with multiple tabs running in parallels. And what is a process? It is basically an instance of a program running on a computer. So say when you run the Rust program, a process is launched. This is the mechanism through which the operating system do things in parallel, such as running multiple programs at the same time. So it's how you can run your Rust programs while browsing your browser. Next, let's talk about multi-core machines. So for the purpose of this lecture, we will say we will use processors and CPUs interchangeably. So a multi-core processor is an integrated circuit with two or more processor cores attached for performance. This is a lot of words, but what they do is that they basically allow multiple processes to execute tasks in parallel. But normally we don't use, for a single program, we don't use multiple processes because they are very expensive, as each process represents an entire program. So they're not needed for tasks such as calculating the user's ages. So can we still achieve parallelism within a single process? So that's why we have threads. Threads is basically short for threads of execution. At a low-level view, there are a set of instructions the CPU will execute. And a high-level view, a thread is simply a set of code. The interesting thing about threads is that they can be run in parallel to each other in a program or process. So a program may have multiple functions on multiple threads running in parallel, instead of just a single function running at any time. They are very useful for when you want to execute tasks in a program. So say you want to run thread per core, and if a program have multiple threads running at the same time, we can execute more code in that period of time than if we only had one thread, when one thread is what we have basically been using so far in this class. And threads are also what we will explore for the rest of this class. How to actually use them in Raster. So this is a very simple example of how to use threads. As you can see from the example code on the right here, we have the function main, which will print hello from the main thread, and a function second thread. Why do we name it like this? We will explain later. which will print hello from another thread. And this line of code here. So what does thread colon colon spawn actually do? Well, it spawn a new thread. And we pass in the name of this function since each thread in Rust is represented by a function. So the diagram on the left illustrates what this actually achieves. At the start of the program, we have just set the main thread associated with the main function. At one point, we call thread spawn, which will create a new thread running in parallel to our main thread. And this could be called by invoking the second thread function. And while these two threads are running in parallel, the main thread will attempt to print this line and the other thread will attempt to print this line. So we basically have two functions on two threads here running in parallel, doing their own stuff, which kind of fits our definition from earlier. Let's look at that example in code. So this is basically that example from the slides. And let's try running this and see what happens. So as you can see here, you still see those two lines print out. And do note that this function second thread will execute on a separate thread. So it will execute parallel to the main function, which is why we have this hello from the main thread print out before the hello from another thread. And let's try executing that again. Oh, look, we only have this line print out. So something weird is happening here. So apparently the thread associated with this function is not running. Why is that the case? We will look at it after this. Also, one thing to note here is that since the thread of colon clone spawn function takes in a thread as an argument, we only need the name of the function. Since this function takes in another function as an argument, we only need the name of the function. So we don't need to do cross parentheses like this. Since this will execute the function and return and pass in the return value to the spawn function, we need the function itself, not its return value. So that's why we only use the name of the function here. And let's continue on with our slides. So here's an explanation for why we only had the main prints out from earlier. So each program has a main thread. As we already saw, we have a main function with a thread associated with it, and the program always finishes when the main thread finishes. If the main thread finishes while other threads are running, the program will still end. So that's why we only saw the main thread print out earlier. It finished before the second thread managed to actually run. And so the second thread never got to actually print out its print. How do we ensure that the second thread will finish running? Well, we can destroy them in the main thread. So in the example code here, first we still spawn the second thread as usual, and then we try to print line. And then here we do something, so we basically call joy on the second thread. And then what this function will do is that it will wait for the second thread associated with this function to finish before continue executing the main thread. So the diagram on the left illustrates what's going on. First, we start with the main thread, which at one point called thread colon spawn. which will have the second thread execute in parallel. Both will try to print. And after printing this line, the main thread will call join, and the main thread will stop executing. It will wait for the second thread to finish executing before continuing, before it will return. So as you can see here, as you can see from the earlier slides that the handle here, the variable handle is the type join handle. What actually is a join handle? Is just a struct that gives you permission to join on a thread. So for example, when we spawn a thread, we need a join handle to actually join it to our current thread. It allows us to block the current thread, as we already explained, until the joining thread terminates. So here, the join call on the join handle will block the main thread until the second thread terminates. And the function thread colon spawn actually returns a join handle to the thread that you just created. So when you call thread colon spawn, we will return a handle to the main thread, which main thread can use to join the second thread. And finally, we have the function dot join parentheses on the join handle. So it blocks the current thread until the thread associated with handle finishes. So this join function blocks the main thread until the thread associated with the variable handle, that is the second thread here, finishes. And if the associated thread panics, an error is returned, otherwise OK is returned. So the join function basically returns a result. It can also return the thread function's return value in the OK variant. So say the second thread, instead of returning nothing, we actually returns an integer. Then this OK variant will contain an integer. And let's look at that example in code. And that is basically the example from the slides. And let's try running it and see what happens. Yeah, and as you see here, we have two prints: hello from the main thread, and hello from another thread from the second thread. And here we still see the typical example of two threads running parallel, even though it looks like we call the second thread before executing this line. This line will still be printed before this line because they are running in parallel. And let's try running it a few more times. As you can see here, both of these threads will always print, because instead of just letting the second thread die, as we see from the early example, here we actually wait for it to finish. So both threads will have executed all the code by the time the program finishes, which is when the main function or the main thread returns. A little bit more on threads. So here we see a code that is very example from the one from earlier, except we call join before printing out hello from the main thread. So what happens here is that this code always prints this in this order. First is print hello from another thread, and then it prints hello from the main thread, which is not what we expect, since if these threads if these two prints were truly executing in parallel, they should print in any order. But here, hello from another thread will always print first. Why is that? Well, we can look at the diagram here. First, we have main, and you execute thread colon spawn. And then the second thread will call hello from another thread. But what happens in the main thread is that after calling spawn, we immediately call join. So that will wait for the second thread to finish it. Only after that, we try to print out hello from the main thread. So by the time we call this print, the second thread will already have finished. So hello from another thread will always print first. So the relevation here is that we can use join function strategically to force an order of execution on threads. So here we force this second print, so hello from another thread, to print before the first print, hello from the main thread. Even though if they are executing in parallel, we would expect these two lines to also try to print in parallel. So there should be no order, but we actually have an order here by doing the join and waiting for a second thread to finish before we print in the main thread. Let's look at that example in code. And this is that example. And let's try printing it out and see what happens. Oh, and as you can see here, the second print actually prints first. And let's try running that a few more times. So nothing changes. We have a forced order of execution here. In that, the second print will print before this print. Also, can threads we already spawn even more threads? Well, agree, yes, you can actually do that. So just imagine a tree where spawn threads are child nodes to threads that spawn them. And a child thread can be joined by the ancestor threads. And here's example in code. We have a main function, we have a second thread function, and we have a third thread function, which prints out hello from that another thread. In the main function, we spawn the second thread, and then we try to print out. In the second thread, instead of just printing out right away, we actually spawn the third thread first, and then we print out. And then both main and second thread will wait for their child threads to finish before returning. And then the diagram on the left illustrates what's happening here. So from the main thread, we spawn the second thread, which will spawn the third thread. And all these prints will print out in parallel. And on the second thread, after it prints, it will wait for a third thread. And the same thing for main, which will wait for a second thread before returning. And let's see how that actually plays out. Right, and let's try running the code. As you can see here, we see that three threads actually print out. So the main thread, even though we call second thread first, it will print out first. And the second thread will print out, and then the third thread. Uh, to better illustrate the concept parallelism, let's do something interesting here. What if we force the second thread to wait 1 second? So we call the physics function sleep, which basically tells the second thread to sleep. And then we tell it to sleep before try printing out. And then let's see what happens. Here we see yet another thread prints out before another thread. Why is that the case? Because while this second thread is still sleeping, the third thread already printed out its print. And so this line hello from z another thread will print first, followed by the line z from another thread. Now let's try telling the main thread to wait for 2 seconds and see what the order print this time is. And it's sort of what we expect. The third thread doesn't have to wait at all, and so it prints first hello from yet another thread. The second thread has to wait 1 second, and so it prints out the second hello from another thread. And then since the main thread has to wait another whole 2 seconds, it prints out last. So that example is illustrating how these threads actually run in parallel instead of consequentially, as if you just invoke the function instead of calling new threads. Next, let's take a little look at closures. What is a closure? So a closure is basically a special function that you can save as a variable or pass directly as arguments to functions. So it's kind of similar to how we pass the function name as an argument to the spawn function. So the example on the left here is an example of a closure. We have the variable example closure here, and then we assign to it this weird value. So what does this value represent? So these two bars here represent the argument of the closure or this special function. And then inside the curly braces is a body of the closure or the special functions. And this special function will return the value 3. So this closure is a special function that takes in no argument since the argument part is empty and returns a value of type i32. You can also see that from the type signature from the type of the variable here. We have a function that takes no argument and it returns an i32. And then we can call this variable as if we just called a function. So here we print out closure returns and we call this variable or this function, this closure, by just calling it as if this calls a function. We just put the name and parentheses. So it calls this closure and returns a value 3. So this line will print out closure returns 3, since the return value of this closure is 3. So some properties of a closure. A closure is anonymous, so it has no associated function name. If we assign it to a variable though, it may have a variable name, but we have no function name as opposed to normal functions where we have to define them with a name. And a closure can capture, meaning it borrows or take ownership of variables from within the scope they're defined. So and whether a capture is a model or taking ownership is inferred from how the closure uses a variable. Here we kind of have a rule of least privilege here. If a closure only needs a reference, then capture through reference, otherwise ownership. So here on the right is an example illustrating the concept of capture. First, we define a variable example vec that is a vector containing the values 1, 2, 3. And we have another closure, the example closure here. Except here, you can see that even though this closure takes no function arguments, we can still access example vec inside the closure. And how does it do it is the closure just captures the variable example vec. And here, since we only access it through indexing, the closure here only needs a reference. So this closure captures the example vec by taking a reference to it. And then when we call the closure, it will return the first value of example vec, which is the value 1. And so this will print out closure returns 1. Let's look at that example in code. And this is basically the second example from the lecture. And let's try printing this out and running this and see what happens. So here we see closure returns 1 because this closure it returns the first element in the example variable that it captured to reference. And the first element is 1, so it returns 1. And so this line will print out 1. And here's basically an example of capturing. How is closure relevant to thread? Well, it's because most commonly in Rust code, a closure is passed into the thread called spawn function instead of a named function. Instead of the normal function that you define, because the closure has the ability to capture variables, and we also have less verbal code. So on the left is the example we have from earlier where we call thread colon spawn, and then we passing the name of the function second thread. So here, instead of defining the function second thread with a name, we can just call spawn and then pass in the closure. So this closure also takes in no function, no closure argument, similar to the second thread function. And it also prints hello from another thread. So also the same as the second thread function. So this closure does the same thing as a second thread function, except the code is shorter. And then other than that, we still do the same thing as from earlier, where the main function will print. Here is an example of spawning multiple threads. Here, we try to print out the values 1 to 10 by spawning 10 threads and then print out each value in one of those threads. So let's look at what this code actually does. First, we declare a vector of join handles. Remember that join handles allow us to actually join a thread instead of just letting them probably die before after the main thread finish executing. And then for values from 1 to 10, we spawn a new thread and then pass in a closure that captures the integer. And then we pass the join handle into the vector join handles. And then at the end of the main function, we have to join the threads we created by just iterating through the join handles and then joining each of them. And let's try running this code. Oh, look, our code doesn't compile. So let's see what does Rust have to say about this. So it say that the where the variable I that this closure captures. So what it's saying is that a reference to this variable made our leaf I. Wait, this sound kind of weird. Like, since we have a third here, that will make no assumption about whether that will always assume that the variables we capture will outlive everything outside of it. So it will outlive everything in the outside scope. So here, that tells us that the border value may outlive the value I in the for loop, and which is potentially very bad because from that perspective, if the border's value actually outlives the original value, then at one point the reference will become invalid. So what is our solution here? What if the closure captures is not a reference, but an actual value? How do we do that? Well, we cannot do that with this code because remember the rule of least privilege. Here the print line only need a reference, and so the disclosure will only capture a reference. But we can force the closure to take a reference or a to take ownership or make a copy of the variable instead by using the move keyword. And then let's try running that again. And here we see the threads actually printing out the numbers. So since the threads are running in parallel, the numbers print out in no particular order. We have 3 and then 5 and 6 and 4 instead of 3, 4, 5, 6. And then we have 1 and 2 instead of 1, 2, 3. And then we have 8, 7, 9 instead of 7, 8, 9. So there's no particular order because all these threads are running in parallel. So the key was a move keyword, which forces this closure to actually copy this variable, this actual variable I here, instead of just taking a reference to I. So even if we join the threads, Rust will always assume thread closures will outlive the outside variables, the variables in the scope that the closures are defined in. And then this reference to them will become invalid. And actually, so the solution is to force the closure to take ownership instead of references. And that's why we have the move keyword. It forces a move of the data into the closure. What the move keyword actually does is that it either transfer ownership of the data into the closure, or it copy, not clone, copy. Any data that can be copied into the closure. So for the example from earlier, the move keyword force a copy of the variable I in the loop, which was an integer. And so it could be copied and the value was copied instead of transferring ownership. And here's an example. This move here force this closure to copy the variable I instead of just taking an ownership to it. If we didn't have move, since we only print the closure, we only take a reference, which since the closure is executed in a new thread instead of just in the main thread, that will always assume that the reference could become invalid, which is very bad. And that's why we have the move here. Now that we know how to use threads, we can actually tackle the opening example. And for this example, we also make use of join to get the thread closure of functions return value. And here's the code. First, we have the current year, which is 2024, and the vector of customer birth years, which is 1992 to 2005. And then we have a vector of customer ages, which for the moment is empty because we haven't calculated the age for anyone yet. And then we have a vector of join handles to actually join or wait for the threads we use later. Here we create several groups out of the list of customer, and each group will have 4 customers each by through these 3 lines of code. And then for each of those group of 4 customers, we spawn a new thread in which we have a closure that move, and for each group, we basically calculate the age by subtracting the birth year from the current year. And then we return a vector of i32 containing the ages. And then for each of the handle, so each of the handle to those threads that we spawned, we call join on them. And here we see the OK variant will contain the closures return value. In this case is the vector of ages. And then we can append this vector to our customer ages vector, which is the vector containing the ages for every customer instead of just a single group. And then when we have already waited for all of the threads, we will print out the customer ages. do note that here, even though, so here, this move keyword force a copy of current year with I32. And that's why we can use current year in this closure. Let's look at how that function plays out in code. So here is that example. This is the code we saw in the lecture, where the all of the data we initialize, and then we split the customers into groups of 4. And then we spawn each thread group, where each thread will calculate the ages of customers and then return a vector to them, vector containing them. And then when we join the threads, when we join the threads, the join function will also return a vec of I32, that is a vec of ages in the OK variant. And so we can append them to the customer ages. And so for this entire block here, the high level idea is that we just collect the data from each of those groups and then group them together into our overall vector. Now let's run this program and see what happens. And we see a list of customer birth years here, 1992 to 2005. And the customer ages are actually correct at what we expect, 32 to 19. So in this code, we can see a pattern where we have the data. We split the data into groups through this slice of code. And then we do computations on each group in separate threads using this lines of code. And then we collect them into our overall result using these lines of code. And the pattern that we had is a very common pattern. It's called the map reduce pattern. What this pattern entails is we have 3 steps. First, we split up the computation into different parts. And in our example, we split our users into different groups, each having 4 members. And then we create parallel running threads to perform the computation at the same time. This is a map step. In our example, we created threads to calculate ages for each user group. So each thread will perform the computation for each part from step 1. And then we combine the results of each computation at the end. This is the reduce step. So in our example, we waited for the result of each thread, and then we combined the user ages into a single vector. And that was an introduction to thread. You explore threads more in homework 11.